Good to go. All right. Do you guys have any questions?
I'm just gonna ask if you do one more problem, like the ones that we don't go off on, where it's like going to 0 and the answer is infinity.
We're gonna keep doing that because we're gonna talk about vertical asymptotes now. Any questions? So let's see. I see you in the homework. Some of you are struggling with the average rate formula. Why is that? I've seen like 3 questions about, when you need to find the average velocity. And it looks like you guys are not getting the answer. Do you know how to find the average rate of a function? So in case that you don't remember, let me just pull up. I just answered one in the morning today. And, it's just a formula. So you just plug in. Let me just put it here. So first of all, please don't do this anymore. Oh, wait. Let me check this, that way it stays in the recording as well. So don't do this anymore, okay? If you want to ask a question, tell me what is your question. Don't just pause this here and then don't write anything. I don't know what you want. Okay? I mind that you want to know everything about the question, but that's not what's supposed to be. But you need to tell me what did you try? Where are you stuck? What's the issue? What's the problem? Okay? Don't do that. Okay? What's your question? I don't know what you want. But just in case, I imagine what's going on. It's just that you don't understand how to do this problem. This is just an average rate of change problem. Okay? And this is the formula. So given a function defined with an interval, closed interval, if you want to find the average rate of change from A to B, so over this interval, that's just the slope of the line that connects the point A comma f of A and B comma f of B. And this is how you find the slope, y2 minus y1 over x2 minus x1. Here the y's are the value of the function and the x's are the points. Yes? So in this problem, all you have to do is, you need to do this 5 times. So your interval is 10, 11, so your A is 10, your B is 11. And your function is the height function. And as we mentioned last week, when you find average velocity, that's just the average rate of change of the position function, which in this case, the position function is the height function. Do you understand this? So this problem is just compute this 5 times. And there is another one that you have to do something similar, and then you have to observe what's going on with the slopes, and then maybe you can make a guess what those numbers are approaching to, okay? Which is the instantaneous velocity. And then you write that down, okay? That's all. Also, since I'm here, let me just bring up another question. Was it this one? So this is the one that I'm saying, you do the same thing. You find the average rate of change, and then when you take a look at these numbers, then you should be able to make a guess what happens when t is equal to 1. Notice that here we're getting closer and closer to 1. So this is 0.1 second, then 0.01 second after t equals 1. So this is from 1 to 1.1, then from 1 to 1.01, etc. So the time interval is getting smaller and smaller and smaller. Okay? So what happens when the time interval, the difference of the time approaches 0? In other words, at t equals 1, that's the estimate that you need to say here. Okay? It's just a numerical limit. We're going to give a meaning to this in the next chapter. Okay? And let's see, I want to talk about, okay, this one. Seems to be some confusion about this problem. So, first of all, I want you to understand something. Math is a language. Okay? So when you read this, you need to understand what the question is saying. If you understand what this question is saying, it should be pretty easy. Okay? As I suggested in one of the comments, draw a picture. If you draw a picture, it should be pretty straightforward how to do this. So what do I mean by that? We have a function, right? So y equals 4 over x. So let's draw that so you can see what's happening. And again, this is just to prepare you what's coming in the next chapter. In the next chapter, this is what we're going to start doing. This is the idea that we want to explore. Okay? So you have the function 4 over x. That's just 1 over x with a vertical stretch. So I'm just going to draw this. We don't really care about this part, the negative part, because all the numbers that we're plugging in are positive anyways, okay? So we're working on this piece over here. This is your function 4 over x. And then we're given the point 1 over 4, comma 16. Indeed, if you put 1 over 4 here for x, you get 16 for y. Do you understand this? So let's say, I don't know, let's say that 1 is over here. So 1 over 4 is here. Okay. So we're given this point on the graph of the function. This is where we are so far. And then it says, suppose that Q is the point x comma 4 over x. What is this? It's an arbitrary point on the graph. If you give me an x, what's the y value here? What's the y value of this point? 4 over x, right? Whatever that is. So that's just a way of telling you Q is a point on the graph. Okay? Q is a point on the graph. And then it says find the slope of the secant line PQ for the following values of x. So this point is called P. So the idea here is the idea. What's happening, if you look at the x values, what's happening to the x values? So we have the point P, x equals 1 over 4, right? Now, if you look at these two values, what can you say about these two values? 1 over 4, by the way, is 0.25. Okay? So what's happening here? What is this number?
It's increasing.
Okay, let's see. So what is this number?
0.35.
And then this one?
0.26.
So what are we doing? Okay. Here is 1 over 4 or 0.25, right? First point is over here. Second point is over here. What are we doing? We're getting close to this from the right. Yes? Now, the next point, what is it? 0.15. So we're over here. What's the other one? 0.24. So what are we doing? We're getting close from the left. Do you understand what's happening on the x-axis? So we have this point, 1 over 4 on the x-axis, and we're getting close to it from both sides. That's what these values are doing. Now, what we're going to be doing is we're going to be watching out for the secant lines, and we want to compute the slope of all of these lines. Okay? Let's look at the picture. So let's see. 0.35. Okay, whatever. I'm just going to say this is 0.35. And let's say that this is 0.24. Okay? So that means that I'm going to have a point here. I'm going to call this Q1. Okay? I'm going to call this one Q2. And then just to change the whole thing, so let's put 0.15 over here. That's going to, okay. So let's just make this more comfortable for us. I'm going to call this one Q3. That's my third point. And then, what is 0.20? Oops. Then 0.24, I'm going to put it here. Let's call this one Q4, okay? Good. Okay, so now we need to look at the line PQ, okay? And we're interested in the slope of that line. So basically, it's going to be a little bit messy now, okay? So I'm going to connect P and Q1, that's my first line. Okay? I'm going to connect that. And you're going to compute the slope of that. Let's call this M1. Okay? The slope of this, let's compute it. And you know how to do it. You have the 2 points, right? To find the y of Q1, just plug in 0.35 in here and you get your y. Do you understand this? So you find the slope of this line. Now repeat the process with the next one. So whatever M1 is, you put it here. Now we do it again. We have this. I don't know if that was straight line. Okay, it's not supposed to go to that. Or maybe it goes, but anyway, the point is that it's too messy like this. Okay, I'm just gonna keep it like that. Let's call this one M2. Okay, and then you're gonna do the same thing from the other side when you do it from the left. But let's keep it from the right so you can see what I'm trying to say. Now, if you look at the last question, it's telling you based on the result, guess the slope of the tangent line at the point 0.25, 16. So at this point, there is a tangent line. So there is this blue line, which is the line that is just touching the function at this point. Okay? So let me clean this up a little bit more. So here is your point P, and so far this is what we have. This is the tangent line. Okay? This is the tangent line, and we are after the slope of this line. And the strategy that we're trying to follow is, okay, I don't know what this is, but what I can do is, I can pick a point here, and then I compute this slope. Then I'm gonna make this point get closer and closer to the one that I want. And then I compute this slope. If we keep doing this, and if we are moving on the curve towards this point, what do you think is gonna be happening to the slope of the secant lines that we're getting? What do you think those lines are getting closer to what? They're going to approximate the tangent line. The closer this point is to this one, the line that I draw is gonna be very close to the blue line. Do you understand this? So this is a limiting process. So if you want to understand the slope of the tangent line, one approach is, okay, just start away from the point and then start working your way towards the point that you want. And observe the slope of those lines. And because these lines are going to converge eventually to my blue line, then these slopes are going to get closer and closer to whatever M is. Okay? And the point is that with the first two, you're doing it from the right. The other two, you're doing it from the left. You know, it's the same thing if you come from above. You get another family of lines that they go towards the blue. Okay? This is what we're going to be doing in the next chapter when we talk about derivative. That's the definition of the derivative, the slope of this line. And it's just this limiting process. The limit as x approaches a point of f of x minus f of a over x minus a. This is how we define the derivative of the function at a. We'll talk about this next chapter. Here is so as you have an idea, an understanding of what's happening. You start thinking about this, so when we come to this, it's not something new to you. Okay? So, but anyways, you know, here you don't really need to draw the picture. All you have to do is find the point Q, put the slope. Find the point Q in this case, put the slope, and so on, and then you make your guess. But it's easier if you draw a picture, easier in the sense that it will give you more understanding of what's happening. You just have a bunch of secant lines, and they're getting closer and closer to this tangent line, the blue, okay? Which is the one that you want to estimate. Why? Because and why do we want the slope? Because once you know the slope, you can find the equation, because we already know the point. The point is 1 over 4,16. And as you know, if you have a point and the slope, that's all you need to understand the line, okay? So once you get the slope, then you can find the equation if you want it. So that's important for this problem, okay? That's why in my comment here I said, draw and you will see what's going on, okay? Basically, all you have to do is use the slope formula to compute each of those values, okay? But it will be beneficial if you draw the picture, because you will gain an understanding on what's happening. Okay, so I just wanted to make those little comments. Let me just get back. Let's continue here. Okay, so last time we were talking about infinite limits. So remember, the last thing that we discussed was infinite limits. Those are limits that give you infinity when you get close to a certain point. Okay? When x approaches a number, then the values of the function grow bigger and bigger and bigger. We say it's infinity or negative infinity, depending if the values are positive or negative. Okay? And now, as you know, if you think about the graph of the function for a second, that means that at that point at which the function is going unbounded, we actually are in the presence of a vertical asymptote. Okay? So let me define this. So vertical asymptotes. Okay, so definition. So suppose that we have a function. So this is the definition of vertical asymptote. And remember, here we are recollecting tools that we're going to use later, because our ultimate goal is to take a function and graph it. Okay? And the asymptote information is important for the graph of a function. So I'm going to be abbreviating this by VA, whenever I need to write this word again. Okay. So let f of x be a function. And a be a real number. Okay. Then the statement is if the limit as x approaches a from the right of the function equals either positive infinity or negative infinity. Okay, so just one type of infinity. Typically, I would just write plus or minus, but I'm writing like this so you see more explicitly. So if the limit from the right is one type of infinity, or perhaps the limit from the left is one type of infinity, okay, it doesn't have to be both. Only having one limit behaving like this is enough. So if this happens, then we will say that the line x equals a is called a vertical asymptote. Okay? Then if this happens, then the vertical line x equals a is called a vertical asymptote. Okay? So you encountered already this idea when you were studying rational functions back in pre-calc. Okay? But it doesn't have to be for rational functions. For example, can you tell me another function that has a vertical asymptote? That's not rational. Give me a function that's not rational and has a vertical asymptote. Yes?
Y equals 1 over x.
Okay, that's a rational function. Remember, rational functions are functions that look like a fraction where the top is a polynomial and the bottom is a polynomial. Right? And you study all of those back in pre-calc. So my point is that those are not the only ones that have vertical asymptotes. So give me another one that has a vertical asymptote. That's not rational.
Doesn't cotangent?
Whichever you want. Just tell me a function and then see.
The logarithm function.
The logarithm function, right? What happens when you get close to 0 from the right? What happens when you get close to 0 from the right? For the ln function, for example. It goes down to negative infinity. Think about the graph of the function, okay? So the line x equals 0 is a vertical asymptote for the natural log function. The cotangent function has also asymptotes whenever the bottom is 0. Cotangent is cosine over sine. So anywhere the sine equals 0, you're going to have a vertical asymptote. It has infinitely many, actually, okay? And multiples of 5. And there are many other functions, okay? I guess we can give you some little example here. For example, f of x equals ln of x. You know, if you remember the graph of ln, remember you need to know your basic graphs. Okay, this is how it looks. So when you get close to 0 from the right, it goes down to negative infinity. So limit as x approaches 0 from the right of ln of x equals negative infinity. So that means that the line x equals 0 is a vertical asymptote. Do you understand this? And remember what this means. Here we're saying that when x is very close to 0 from the right, the values of the function are getting smaller and smaller and smaller without bound in the negative direction. Okay? In particular, it means the limit does not exist. But we write the infinity information because it tells you something about the function. And then your class may also mention cotangent. Let's put it here. Okay, I'm going to put tangent because tangent is usually used more. So let me just put tangent. And if you want to see what happens with tangent, remember that tangent is sine over cosine. Okay? And every time that you see a fraction, you know that whatever makes the bottom 0 is something that you need to worry about because it's not part of the domain. But if the top is not 0, then what happens is that you're going to have a number over something that's approaching 0, so you're going to get infinity. Yes? So anywhere that and whenever cosine approaches 0, what happens to sine? What does sine approaches when cosine approaches 0? 1 or negative 1. Unit circle. Think about the unit circle. You have the unit circle here. What's cosine? Giving a point on the unit circle, what tells you cosine? So let's say that this is your angle x. What are the coordinates of this point? I said this last week. What are the coordinates of this point? Cosine, comma sine. Okay, guys, if you don't know this, you need to study this. Okay, it's something that you need to know from before. This is the second time that I say. Okay, you need this if you want to be able to analyze functions. Whenever a trigonometric function shows up, this has to be in your mind because you may need it. Okay, so any point on the unit circle, by definition, the x value of the point is given by the cosine of the angle, and the y value is given by the sine of the angle. Do you understand this? That's the definition. So we want to know what happens when cosine approaches 0. That means you have to watch out for the x value of this point. So when is the x value of this point approaching 0? Here, right? Because that means that the point must be on the y-axis. So cosine is 0 at these 2 points, right? And whenever cosine is 0, that means that the sine would be either 1 or negative 1. Do you understand this? So when you get close to that situation that makes you cosine equals 0, the top is either 1 or negative 1, so we know this would be some type of infinity, either positive or negative infinity. Okay? So vertical asymptote is going to show up. Moral of the story, if you have a function that's defined as a fraction, it doesn't have to be a rational function. If you see a fraction and you're looking for vertical asymptote, you should always worry about what makes the bottom 0. Because if the top is not 0 at that value, then you have a number over 0 that's infinity, as you know, in the limit. Okay? So those are your candidates. So if you want to, and remember, this point here is pi over 2, and this one was 3 pi over 2. Okay? So here, if you are looking for vertical asymptote, we need to wonder when is cosine 0. And as you know, this happens at pi over 2 and 3 pi over 2. And they're coterminous, right? So pi over 2 plus 2k pi, or maybe 3 pi over 2 plus 2k pi. And we can actually nicely combine these. Because the first one is just saying this point and just going around full revolution and stopping here all the time. And the second one is saying the same thing. Start down here and then full revolutions and stop here all the time. You can combine these two solutions nicely. You can start here and then jump from here to here, then from here to here, and so on, back and forth. And you do that by adding pi's, right? If you're here, you add pi, you end up here. You add pi again, you end up here. And in other words, I'm going to be combining these two by adding multiples of pi. That's typically what we do. Okay, pi over 2 plus k pi. I'm basically just combining these two solutions in one. Okay, instead of just going around the top and stopping at pi over 2 at the time, and then going around in the bottom, stopping at 3 pi over 2 at the time, we jump back and forth. Top, bottom, top, bottom. That's what I'm doing. Okay? Here, k is an integer. And at those points, I already know what's going to happen with the top, which is 1. So, for example, let's pick from the first family, I'm going to pick pi over 2. And from the second family, I'm going to pick 3 pi over 2 to investigate the limit, okay? Just for formality. So, for example, limit as x approaches pi over 2 of the tangent function. Notice that the definition of vertical asymptote, you don't have to look at the full limit. You just need to look at the side limit, okay? Because sometimes a full limit may not exist. If you think about this function, the 1 over x equals 0 is a vertical asymptote, yes? But the limit at 0 does not exist. Notice that from the right you go to positive infinity, but from the left it goes to negative infinity. So the actual limit does not exist. But it's enough to just look at the side limit. That's why in the definition we have the side limit. Okay, so I don't know. Let's do it from the right. The limit as x approaches pi over 2 of the tangent function from the right. So x approaches pi over 2 from the right, or sine over cosine. So what will be this limit? Let's see. We know that when x is close to pi over 2, sine approaches 1. That's not a secret. So this goes to 1. And then we know that cosine is going to go to 0. Now we just need to see, are we doing it positively or negatively? So what do you think? Are we getting close to 0 with positive numbers or with negative numbers? So let's see. Let's go to a picture. What does it mean to approach pi over 2 from the right? What do you know about x here?
Greater than 0.
Greater than pi over 2.
Right.
Right? It's to the right of pi over 2, so this means x is bigger than pi over 2. What does that mean about the angle? In what quadrant is it? We did this analysis on Monday. This means that x is in quadrant 2. Yes? We are analyzing cosine. What do you know about cosine in quadrant 2? Is it positive or negative? Negative. So we're getting close to 0 with negative numbers. Do you understand this? So what type of infinity do we get here? The top is positive 1. The bottom is close to 0 but with negative numbers. So this is an infinity, but which one is it, positive or negative infinity? Negative infinity. Does it make sense? Yes? All right, so that means that the line x equals pi over 2 is a vertical asymptote. And actually, not just that one, pi over 2 and all its coterminals. So all this entire family are just vertical asymptotes, okay? So I just say, so in particular, the collection of pi over 2 plus 2k pi, where k is an integer, this collection, these are vertical asymptotes. That's what we get from this computation. Now let's do the same thing for the other family. So now I'm gonna do limit as x approaches 3 pi over 2. Let's see how you wanna do it, from the right or from the left? From the left? Okay, do it from the left of the tangent function. So every time that you want to analyze tangent, unless you remember the graph of tangent immediately, I strongly encourage you to write it as sine over cosine, okay? It's easier that way. And if it was cotangent, you write as cosine over sine. So it's the same idea. Okay? All right, let's see. So when we're approaching 3 pi over 2, what do we know about sine? What is it approaching to? Negative 1. So this top here approaches negative 1. It's a number. And when we approach 3 pi over 2, we know that cosine approaches 0, right? So the moment that you say this, you already know that we're going to be writing some type of infinity here. Now our job is to decide which one is it. Is it positive infinity or is it negative infinity? To do that, you need to know this guy here, because the top is negative. We know that. The question is, what about this guy? Are we getting close to 0 with positive or with negative numbers? The only way to know that is to understand where is this x. By that I mean, what's the quadrant of this x? Okay? And that information is encoded here. So what do you know about x here? With respect to 3 pi over 2.
It's greater than 3 pi over 2.
Is what?
Greater than.
Are you sure?
Less than.
Remember, you're approaching from the left, right? So it's less than. So this means that x is less than 3 pi over 2. What does that mean? What quadrant are we? This means that x is in quadrant 3. Does everybody understand this? So if you look at the picture, that means that we're approaching like this. Okay? We're approaching like this to 3 pi over 2. Before we were doing it like that. We're approaching it from the right, like that. The value is big. Right? Now we're approaching 3 pi over 2, like this. Yes? Okay? So we're in quadrant 3. So what do you know about cosine in quadrant 3? Cosine is negative, so that means that we're approaching 0 with negative numbers. So now the top is a negative 1. So negative 1 over something approaching 0 with negative values. What is that? Positive infinity, right? If you would have picked from the right, what would be the answer? If you would have done from the right, I mean, it was a choice to do it from the left. If you would have done it from the right, what would have been the answer? Negative infinity, because now you would be quadrant 4, right? Because you would be approaching 3 pi over 2 like this from quadrant 4. Yes? And cosine is positive there. Do you understand this? And then negative divided by positive will give you negative infinity. But you don't have to do it from both sides, just one of the sides is enough. So because we have an infinity here, then this means that x equals 3 pi over 2 is also vertical asymptote. But moreover, everybody in this family is also a vertical asymptote. You understand there are infinitely many values here, right? For each integer, you add a multiple of 2 pi and you're gonna get a new number. Like for example, this 3 pi over 2, then when k is equal to 1, you add 2 pi, so it'll be 7 pi over 2 is plus 4. 7 pi over 2, 11 pi over 2, 15 pi over 2, and all of those guys, they are here. And here, it will be pi over 2, 5 pi over 2, 9 pi over 2, etc. Okay? So 3 pi over 2 plus 2k pi, where k is an integer. These families are all vertical asymptotes. So the tangent function has infinitely many vertical asymptotes. And you know that. I mean, you know the graph of the tangent function, right? How does it look like? Here is negative pi over 2. Here is pi over 2. This is typically the main period for the tangent function, and this is how it looks. It looks like the cubic, right? That's a tangent function, and then it just keeps on repeating to the right and to the left, non-stop. Draw another one. Then here's pi. Here is 3 pi over 2. And you know, the period of tangent is pi, so the length of this interval is pi, and then just every pi it keeps on repeating the same thing over and over again to the right, and over again to the left. So here you can observe, if you approach from the left to pi over 2, you go positive infinity, but we're doing it from the right before, so it goes down to negative infinity. Yes? If you approach 3 pi over 2 from the left, as we did there, as you can see, it goes up to positive infinity. Yes? Okay. All right, so that's tangent. Any questions? Are you okay with this? All right. Notice that what I'm saying here is actually trigonometry. There is barely any calculus in what I'm talking about here. Okay? All of this is trigonometry. Okay, so let's see. Let's just to close this idea. Otherwise, it will be another more day talking about things that we should talk, but not so much because there are other things that we need to do. So I'm going to give you some functions. I want you to find vertical asymptotes. Okay? So find the vertical asymptote of the functions. Of the function, if any. Maybe it has not. Okay? Maybe it has no vertical asymptote. Like polynomial functions, they don't have vertical asymptotes, right? All right, so let's do this guy, and let's do this guy. Okay, I had cotangent here, but we already did tangent, so there's no point in cotangent. Okay, so here we have three functions. Let's go ahead and let's find the vertical asymptotes. So remember, let me just summarize the techniques. You just want to look, the idea is that you should look for candidates. What are the candidates? The candidates are whatever value you think that if you get close to it, you're gonna get an infinity. Now, how you can verify that these candidates are actually vertical asymptotes? You need to take the limit, okay? And figure out that indeed the limit will be infinity from one of the sides. If you have a rational function, like the case of 1 and 3, you can do this the old way, the way that you learned back in pre-calc, which is if you have a fraction, the only way that you're gonna get infinity is if the bottom becomes 0, right? While the top is a number. So what did you do back in pre-calc? You find the zeros at the bottom, right? And those are your candidates. Why do I say candidates and not just vertical asymptotes? Because you have to make sure that those zeros at the bottom are not zeros at the top. If there are zeros at the top, that means that you have a factor, so you need to simplify it first. So what you used to do is make sure that your function is in lowest terms, you simplify everything, and then you look for the zeros of the denominator, okay? And those are your vertical asymptotes. That will work for 1 and 3. It may not work so much for 2, because this is not per se a rational function, because we have this ln in here. We still have a denominator. This is going to be part of our candidates. every time you have a fraction, you should always consider whatever makes the bottom 0. That's a candidate to give you infinity when you take the limit. Because a number over something approaching 0 is infinity. Yes? But you have to look at other stuff. Like here, nothing else could give you infinity. Here, nothing else can give you infinity when you get close to a number. But over here, there's somebody else that can give you infinity. Who can give you infinity over here, other than the denominator? Okay, that's a number, but what term? The ln, right? You know, ln itself has a special point that if you get close to it, will give you infinity. So you should consider that as well. And if you have a tangent in here, or a cotangent, you need to have those in mind as well. Okay? All right. So, find the vertical asymptotes and while I take attendance. But what do we get here? What's the vertical asymptote? X equals -1. So again, you know, don't ignore what you already know. This is a rational function. It's okay to just look at zeros of the denominator. Okay. Now here, because we know more, we can actually verify it. So we know that our candidates. So candidates. In this case, there's only one candidate. Is whatever makes the bottom equal to 0. So 2 times x plus 1 equals 0. So that would be -1, right? So now let's verify it. Let's take the limit, and what are we expecting to obtain when we take this limit? Some type of infinity, right? If we do, then we have a vertical asymptote for sure. Okay, what do we do, from the right or from the left? It doesn't matter in this case. So which one do you want? Left. From the left, okay. And let's use this to practice how to determine the type of infinity. Okay, so when you take this limit, we're approaching -1, so the top is a 1. That's not going to change, right? And the bottom, what is the bottom approaching to? 0. We're approaching -1, so this factor approaches 0, right? So this is 1 over 0. We know we're going to get some type of infinity, right? So you can already say this. Put an infinity here. We just need to figure out what goes in here. Should we put a plus or should we put a minus? Minus? Okay, so let's see. So to know what type of infinity this is, we need to know the sign of this denominator, right? And to know the sign of this denominator, we need to know the sign of x plus 1. Because 2 is positive, we know 2. So what do we know about x plus 1? And the information is here. X approaches -1 from the left. So what does this tell you about x? Is it less or bigger than -1? So x is less than -1, which means that if I move the -1 over, we get x plus 1 is less than 0, right? So because x plus 1 is less than 0, that means this parenthesis is negative times a positive, that's still a negative, so this bottom is negative. So positive over negative is negative. Yes? That's how you determine the type of infinity that you get. Do you understand this? If you would have done it from the right, then you would have gotten positive infinity. Right? Just it would be positive. Okay, anyways, the point is that this then tells me that the line equals x equals -1 is a vertical asymptote. And we don't have any more candidates, right? There's nothing else that could give you infinity in this function, so that's it. This is a vertical asymptote. All right? Now for the next one, what was the next one? The next one is x plus 3 times ln over x squared minus 9. Okay, so what are the candidates here? So let's see, candidates. Let's see, first, because I see a fraction, I already know that one type of candidates that are going to come from that denominator. So I'm just going to do the whole thing, okay? So that will be whatever makes this equal 0. Those are candidates. Whether they happen to actually be vertical asymptote or not, that's a different story, right? So remember, this is x plus 3, x minus 3. So we have -3 and 3. So these two are candidates. If you are already foreseeing what's going to happen is you know that this guy is not going to survive because this x plus 3 will end up canceling with this one, okay? But let's let the limit take care of that on its own. That way we keep practicing computing limits. So those are some candidates. Now, that's not the only thing that you should worry about. This fraction could go to infinity if the bottom approaches 0. Okay, we took care of that already. What's another possibility that this fraction could go to infinity? If this top here, this ln approaches infinity, right? And we know that happens at a special point. What is it? 0. So x equals 0 is also a candidate, since y equals ln of x will approach negative infinity as x approaches 0. Okay? So that's a term that will go to infinity, so we have to negative infinity in this case. When I say infinity, if I don't stress it, it could be positive or negative. Okay? So I don't have to be saying positive, negative all the time. So that's a term that will give me a type of infinity, so we need to analyze it. Okay, so to actually verify this, then let's do one by one. So let's see, negative 3. So we should be computing the limit as x approaches negative 3 from one of the sides. Again, it doesn't matter, so I'm just gonna pick the right. Now, if you need to compute this limit, what's the first thing that you do when you compute limits? Okay, you plug in. So, okay, I just realized something. We should not even be worrying about negative 3. Why? Why?
Because the x plus 3 and then
Yeah, well, when you square it, it will be positive, and then it will be like, I don't know, it won't be.
No, it's a little bit more subtle. It's easier, but more subtle. The why. What's the domain of that function? You have an ln in there. ln doesn't allow anything negative. So if you graph that function, whatever the graph is, there is nothing to the left of 0. Do you understand this? So negative 3 has no business here. Okay? You know, if you want, we could do this, put a square here, and then we can plug in negative 3. Okay? Because now, whatever, let's put the square, that way we, so I don't have to erase this. But if it was just a ln, you would just say, okay, I mean, these are the candidates, but then ignore this because it's not even a concern. We don't have any graph to the left of 0 because ln, the domain is from 0 to infinity. Do you understand this? The domain of the previous function without the square that I put would be from 0 to 3, skip 3, and then 3 to infinity. Right? Because 3 is not good because of the bottom. Right? But anything negative is not good also because of the ln. Anyways, we just solved it now by putting a square here. By putting a square there, now we're allowing x to be negative as well. Right? Because you square it, it becomes positive, so we're good. You okay? Once again, this still applies because if ln approaches, if this approaches negative infinity when x approaches 0, when x approaches 0, x squared also approaches 0, so this sort of behavior will still happen with that function. Okay? So we still have that candidate. Okay, so let's do it now with this example. So I guess I should do this. Let me do this. So I'm squaring the x, not the ln, but the x, just to make sure that. And don't bring the 2 here. That's another thing, because technically speaking, even though that's a property that you can bring exponents down, the function that you get is not the same as the original function. Do you understand why? In other words, ln of x squared, technically speaking, is not 2 times ln of x. Even though in pre-calc you would write that those 2 things are equal. Who can tell me why? Yes?
the domain changes.
Domain changes. What's the domain of this function? Domain is what can you plug in? What's the domain of this function on the left?
Zeros.
All real numbers except 0. The only issue here is 0. Any other number you can plug it in. If you plug in something negative, you are squaring that, so it's becoming positive anyways. You understand this? So the only problem here is 0. How about this one? What's the domain of this one? From 0 to infinity. Right? We can only plug in positive stuff. So these 2 functions, they are not the same. Okay? However, if x is positive, they do match. They are the same. So if you already know that x is a positive number, then you do have equality. So in pre-calc, it was understood that when you use these properties, it's always assuming that your variable is positive. So you can write your equality. Okay? All right. Okay, so, and again, these things are important. The reason why I'm mentioning all of these little details is because you will need all of this information later when we start graphing. If you want to understand a function, you need to know all the little details about that function. Okay? And domain is a very important thing. It's the first thing that you do. Remember, a function is like a machine. Even though we typically don't do that nowadays, when you get a new machine, what's the first thing that you should do? Even though we don't, but what's the first thing that you should do? You read the instruction, right? You need to know what to do with the machine. What can you do, what you cannot do. Otherwise, you can break it. Yes? Well, it's the same thing here. I give you a function. What are the instructions of the function? The domain. You need to know what you can plug in and what you cannot plug in. Okay? So, okay. Anyways, back here. So we dealt with that with that issue. So when we plug in -3, when we approach -3, what happens? The top approaches 0, right? The bottom approaches 0. So that's a 0/0 situation. And as you know, that's an indeterminate form. So something needs to be done. What do we do in this case? Well, let's try to see if we can factor something and maybe simplify. And indeed, we know we can factor, and then the problem will be gone, right? So that's the reason why back in pre-calculus, they told you before you find vertical asymptotes, factor and simplify whatever you can. Okay, so now we see that the x plus 3's, they simplify, and now the factors that were giving us zeros, they're gone. So we now get a new function. And what's the limit of this function? What is this? What is this limit? Just plug in, right? No problem. What's the first thing that you do when you compute a limit? You plug in. You plug in, what do you get? What do you get if you plug in? You don't have to tell me decimals. Just tell me the expression. I mean, if you tell me a decimal, just give me an approximation. One exact answer. What is it?
The natural log of 9/6.
Good. Is that why are you guys quiet? I don't understand why you're quiet. Just plug in. It's a 9, right? When you plug in -3, you square it. So ln of 9 over -6. So you get ln of 9 over -6. And if you want to be fancy, then you can simplify that more. Remember, 9 is 3 squared. So that's 2 ln of 3 over -6. So you can write this as negative ln of 3 over 3. You don't have to, but you can do. Okay? Anyways, the point is, you can stop right there at that point. The point is that we didn't get infinity. Remember, we're trying to figure out whether this number will give me a vertical asymptote or not. It's not going to give us a vertical asymptote because for you to have a vertical asymptote, this limit should have been infinity. Now, maybe the right limit was not infinity. Technically, you should verify the left limit as well. So sometimes the right doesn't give you infinity, but the other one will give you infinity. Okay? But in this case, we know that if we switch to the left, all the same thing is going to happen. So it's just that here we're going to have a positive. Right? Actually, no, we're going to have the same number. Right? If we switch to the left, it doesn't matter. We will just be plugging in -3 anyway. So the same answer will come out if we switch to the left. Do you understand this? We never did really use the fact that we're approaching from the right. Did we? Did we use the fact that we're approaching from the right? No. So the answer will be the same. Since I'm talking about this now, if thinking about the graph of this function, what do you think is happening around -3? There is a hole. Very good. Notice that both limits, the side limits, there will be the same number. Yes? But the function itself is not good at -3. That just means that you're going to have a hole right there. Whatever the function is, it's going to go there, but then there will be a hole when x is -3. Okay? Okay, so the point is that this is not infinity. So it's not positive infinity or negative infinity. And similarly, we can easily see that the other limit of the function will also be the same number. So x equals -3 is not a vertical asymptote. So this candidate is crossed off the list. Okay? Now you know for sure that's not on the list, but also if you wanted to graph this function, you already have a little information. You know that at -3, whatever the y value should have been, which is this one, right? Is the y value corresponding to -3. For the good function, there is a hole right there. Okay? Now we just gain that information. Okay, now we just repeat with the others. Now with the others it's easier because we will get what we came for. We're gonna get our infinity. Let's approach 3. I don't know. I'm gonna do it from the left this time. Okay. Once again, it doesn't matter. Here we're just verifying that we get infinity. Okay. Just to make our job easier, I'm just gonna go ahead and instead of x squared minus 9, I'm going to put the factor expression of it already. Okay, so we're approaching 3 from the left. We're approaching 3. First thing that we do is just plug in. The top will just be a number, right? 6 times ln of 9. That's a number. Whatever it is, it's a number. Yes? The bottom, what's going to happen to the bottom when we approach 3? What do we get in the denominator? We get 0, right? And we get 0 because of this factor right here. So a number over 0, we already know that we're going to get some type of infinity. Our job is to figure out which one is it. But just right now, you can already say, okay, there will be a vertical asymptote. Okay? Because it's a side limit. So there's no, oh, one behavior on one side and another behavior on the other one. I don't care. It's a side limit. There will be one type of infinity. But let's find it. For that, we need to know the sign of the expressions. Let's see, what's the sign of the top? So this goes to 6, right? And this one goes to ln of 9. We know 6 is positive. What about ln of 9? Is it positive or negative? Positive. Remember, think about the graph of ln. Put it somewhere in here. Notice how many times I've used the graph of ln. Okay? This is the graph of ln. After 1 is a positive function. It hits 0 at 1, and after that is positive. Between 0 and 1 is negative. Yes? So ln of 9 is somewhere in here. So it's positive. Okay, so that means 6 times ln of 9. So the top is a positive number. Yes? Because that's what we get in the top. Now the bottom, what is this guy? And you approach 3. That's positive. That would be a 6, right? So that's 6 times 0. So that's the reason why we know that we're going to get an infinity. Now we're wondering, what about this 0? Is it a positive or a negative? Well, let's see. We know that x is approaching 3 from the left this time. So x is less than 3. So that means x minus 3 is going to be less than 0. So this quantity here is less than 0. So the 0 that we're getting here is negative. So if we're approaching 0 with negative numbers, so we have 6 times negative numbers, so this is a negative in the bottom. Positive divided by negative is negative. So that's negative infinity. Okay? Once again, this is not so much for the vertical asymptote question, but just to practice how to find infinite limits. Because if the question would have been this one, not find vertical asymptote, but this limit, you need to do all of this analysis that I'm doing. Because it's not enough for you to tell me, oh, some type of infinity. Yeah, okay, fine. What is it? Is it positive infinity or is it negative infinity? Okay. So this means that we found a vertical asymptote. So x equal 3 is a vertical asymptote. Okay. And now our last candidate was x equals 0. So we do limit. Okay, let me just put the function first, and then remember that we got that candidate from before I even modified the function with the square. Okay. Right now it doesn't really matter how we approach 0. We need to do either right or left, one of the two. We need to put it here. So we're gonna decide now. It doesn't really matter now because of the x squared. But if we didn't have the x squared, if it was just ln of x as originally intended, what do we need to write here? We must write from the right, positive. Because to the left, there's nothing to see. There's no function. Do you understand this? But in this case, it doesn't matter. But I'm going to do it from the right just because that's what it should have been if we didn't have this square. Okay? Okay, now we compute. So let's see what happens. What happens to the top? Just analyze term by term. What happens to this term? 3. What happens to this term? Negative infinity. Remember, when the argument of ln approaches 0, it goes down to negative infinity. Do you have the picture of ln in your mind, or should I show it again to you? Okay, remember, it's this guy. Okay, so when you get close to 0, it goes down to negative infinity. All right, so that's a negative infinity. The bottom, what's this guy? That's a 3, and this one, and negative 3. Okay, so infinity, we have a type of infinity in the top, we have a number in the bottom. Infinity divided by a number is still infinity, right? So we know this is going to be a type of infinity. Let's figure out which one is it. Who can tell me which one is it? Positive or negative infinity? What is it? Positive infinity. Good. The top is a negative, right? And the bottom is a negative. Negative divided by negative, positive. Does everybody see that? 3 times negative infinity is negative infinity. But this bottom is a negative 6. So negative divided by negative gives me a positive. Yes? So we found ourselves another vertical asymptote. So this function has 2 vertical asymptotes and a hole. Just by taking these little limits, now we know several things about this function, okay? And this will be information needed later when it's time to graph. Okay, are we okay with this? All right, so that was that one. Then the last one was, okay, the last one, I'm gonna do a pre-calculus style because it's a rational function and there's nothing wrong in using what you already know. So rational functions, first thing that you do is simplify, okay? So let's factor the top. Who can tell me how to factor this? If we can factor it. Can we factor the top? Okay, what is it?
X plus 4, x minus 2.
Good. X plus 4, x minus 2. On the bottom?
X plus 4, x minus 4. I mean, x 2.
Okay. X plus 2, x minus 2. Good. So, for example, this means that your candidates will be negative 2 and positive 2, right? Because of these two guys. But when you take the limit, when you take the limit at 2, for example, what's going to happen? You're going to get 0 in both places, 0 over 0. And what would you do? You will do this, you will simplify, and then take the limit. And then no infinity in your limit. Yes? You will get whatever this is, 4 over 2. So you're going to get 2 as an answer for that limit. Yes? No, sorry. 6 over 4. So 3 half as an answer for that limit. So we know we're not going to find a vertical asymptote there. And that's what precalculus told you. That if you were looking for vertical asymptote, then you say, well, as long as x is different than 2, this function is the same as this one. And that's good enough. So it means that really the only remaining guy is x equals negative 2. So x equals negative 2 is a vertical asymptote. And just to, which one do you want? Right or left? Is that a problem? I mean, you have been consistently telling me left. So is it more confusing from the left than from the right? No? Okay. Are you left-handed? Okay, so you can put the whole function, but okay, let me put the whole function. I'm going to put the factor version. But as you know, it's okay to put the simplified version. It's okay to simplify. But the point is that that x minus 2 has no business here because negative 2, the 0 is coming from here, so this guy has no business. Whatever we get up here, we cancel with this one anyways. Okay, but that's the original function, so let's take the limit. So when we get the limit from the left, what happens in the top? This factor goes to what? 2. This one? To negative 4. This one? To 0. And this one? Negative 4. Okay, so we have a number on top, right? Namely negative 8. And we have a 0 in the bottom. So we know we are getting an infinity, as expected. So we have a vertical asymptote. But let's go ahead and let's practice. Let's figure out which one is it positive or negative infinity? Let's see. Who can tell me? Is it positive or negative infinity? Negative infinity? Okay, so let's see. Why is this? So we need to figure out the sign of 0. What's the sign of 0? Okay, let me rephrase that because that sounds weird. The sign of the term approaching 0, right? Because 0 doesn't have any sign, right? So the term x plus 2, what's the sign of that? Positive or negative? Remember, that information is right here. It depends how you're approaching negative 2. X is less than negative 2, therefore x plus 2 is less than 0, right? Again, if you write it down, it's easy. X is less than negative 2, so move the 2 over, and you get x plus 2 less than 0, okay? So this guy is a negative, so the top is negative. Now the bottom is a negative times a negative, giving you a positive. So negative divided by positive is negative, right? So you get negative infinity. Did you understand this? Yes? If it would have been from the right, what would have been the answer? Positive infinity. Because it would then be positive, the x plus 2 will be positive, so the bottom will remain negative, and then negative divided by negative will give you a positive. Okay? Alright. So we have computed a lot of infinite limits. Okay, any questions on this? Okay. 40 minutes. I want to do. Okay, so this is a natural continuation of that topic. So let me just go ahead and talk about this one. Okay, so now notice the limits that we have been doing. The answer has been infinity, but we're still approaching a point. Okay, we're approaching a number. When x approaches a number, we see that the function is growing big in the positive or negative direction. Okay. Now, it could also be the case that x is the one that's approaching infinity. In other words, what happens to the values of the function when the values of x are very, very, very big? This is called the end behavior of the function. We call it, now in calculus, we call it limits at infinity, because x approaches infinity. Okay? So, let's talk about that. So, I guess, and you already know some of these from pre-calc. Again, when you analyze polynomials and rational functions, you were asking for end behavior. Remember, you used to graph those functions, right? So you need to know how those functions behave to the extreme right and to the extreme left on the x-axis. Okay? All right. So let me start with an example. So consider the function f of x equals 3x squared over x squared plus 1. And then the question that I want to ask is, what can we say about the values of the function when x is very big, in either positive or negative direction? Okay? So in other words, the question is, are the values of f getting closer and closer to some number when x is very large? Okay, so for example, a fancy way, so in symbols, let me just introduce this immediately. In symbols, the question that I'm asking is, the limit as x approaches positive infinity of the function. You say the values of f. And this is what I'm asking. Okay? What is this limit? And if I want to know what happens when x is very small in the negative direction, in other words, if it goes all the way to the left, similarly, if x is very small in the negative direction, really what I'm asking is what happens when we are all the way to the left on the x-axis. So in symbols, this question will be asked like this. Okay? This is what we call the end behavior of the function. These two questions, this is called the end behavior. You see, here's the other thing. I think this word can be is written in two ways, like that, or with a U, like O-U-R.
That's like
English, well,
British.
I know, but it's English, right? But then there is US English and British English. Anyway, sometimes you may see me writing a U in here after the O. Okay. Okay, so this is called the end behavior of f. You know, we want to know what happens when x is very big. Maybe the function goes to infinity, like polynomials. Polynomials, they either go to positive or negative infinity, as you know. They don't get close to any number. But other functions, they may get close to a number. What happens in that case? If we get a number that's in this answer, what do we have at that number? A horizontal asymptote. That's what it means to have a horizontal asymptote, that the function is getting close to that number when x is very big, either in the positive or in the negative direction. Okay? All right, so let's try to analyze that in here. Let's see, who remembers this one back from pre-calc? What would be the answer to this question? Do you recognize the horizontal asymptote for this function? We're going to see the theorem soon. I'm going to rewrite the same theorem that you saw back in pre-calc. Okay, if you don't remember, then that's okay. We're going to figure it out now. You already have the knowledge. You just need to be creative with your knowledge. Okay, so solution. All right, so we want to analyze the function f of x, right? This function is 3x squared over x squared plus 1. And we want to see what happens to this function when x is very big, right? Let's just focus on x being very big. By the way, it doesn't really matter if we're going positive or negative infinity because the only x's that we have are being squared, right? So we're actually just looking at positive values here all the time, regardless of where you're going right or left. So, doesn't matter. Okay, so what I was saying. Yes, so we want to see what happens to this function when x is very big. Let's think about it. If x is very big, what happens to the top? It's also very big, right? It's actually bigger than x, right? Because we're squaring that and then multiplying times 3. What happens to the bottom? It's also big. So we have something big divided by something big. So this will be infinity over infinity. By the way, this is another type of indeterminate form. Okay? Remember we have 0 over 0. Infinity over infinity is another indeterminate form. So here many things can happen. Okay? This could be a number, or maybe this infinity is bigger than this one, and therefore this one will win, and you will get infinity. Or if the bottom one is bigger than this one, it's a larger infinity, then this will go to 0. Okay? We're going to see examples in which all of those cases happen. Okay, back here, we want to try to figure out what type of infinity, what's going to happen here. This form of the function is not helping me because by just analyzing this, I keep getting infinity on the top, infinity in the bottom. So what I'm about to do is I'm going to modify this function algebraically. And the modification is I'm going to divide top and bottom by x squared. Okay? So typically what you want to do is divide top and bottom by the highest power of the denominator. Okay? Why? Because that's, well, you're going to see why. So when you see something like this, just divide top and bottom by the highest power of the denominator. So that formula is not helping me. So what I'm going to do is I'm going to divide top and bottom by the denominator. Now there is a little thing that I have to say here. these two expressions are equal, provided what?
X squared is not 0.
Very good. Remember, when you divide by something, you have to make sure that that stuff that you're dividing is not 0, right? Now, the thing is that what are we trying to analyze? We're trying to analyze what happens to this function when x is very big. So we're super far away from 0, right? So I don't really care about what happens at 0 because I don't have to concern myself because that's not the question. The question is, I know at 0 this function is 3. But I want to know what happens when x is big. So as long as x is different than 0, this equality holds. And that's fine because we want to know what happens when x is big, anyways, in the positive or negative direction. Okay, so that means that we get a new form of the function, the same function but a new formula, which would be 3 over 1 plus 1 over x squared. By just dividing top and bottom by x squared, we get that this is the same as this. Do you understand what I just did? Simplify, here just split and simplify the two little fractions. Yes? Okay, now let's repeat the question. When x is very big, what happens to this? Now let's look at the correct formula. Is there an x in the top? No. The top is 3, right? That's 3. Now let's work on the bottom. This is a 1, nothing to do about it. Now the x is now in this piece right here. What can you tell me about that fraction? If x is very big, what happens to that little fraction? It's going to go to 0. It's going to go to infinity because you have 1 over infinity, right? And therefore, what's going to happen to the overall function? It gets close to what? If this goes to 0, then what happens to this function? The top is a 3 and the bottom is a 1 plus 0. So what value do you get? What is this? 3. So when x is very big, the values of the function are going to get closer and closer to 3. Do you understand this? And this actually works for any rational function because any rational function, what you have on top and bottom are polynomials. You divide everything by the leading term, you can say leading term, but just the by x to the degree of the denominator. Okay? You don't have to touch this guy. And then you can play this game. Okay? Another way, and I think it's probably easier to look at it that way, is factor. Okay? If you're comfortable factoring, notice that here I could have just factored x squared in the bottom, and you would have gotten this. And then you simplify, and so you get exactly what we have above. Okay? And then you analyze. So, and it's just that in the top there was no need to factor because it was already factored. But here you can take out always the highest exponent, factor it out. Naturally, there will be fractions because the other terms, they have less, the exponent, the degree is less of the other terms. So because this is too high, then you're going to have x's in the bottom. Okay? You're going to see that in other examples. Or alternatively, divide top and bottom by the highest power of the denominator. It's exactly the same thing as what I just did. Okay? This was a side comment. So I guess the answer here would be, answer would be that the values of f, and this is, and notice that whether x approaches positive or negative infinity, we have the same thing because I don't care. Even if this is this would always be positive anyways, but even if this was just x without the square, if it's a negative infinity, it's still 1 or negative infinity is still 0. Okay? So the answer would have been 3 no matter what. Okay, so the values of f get closer and closer to 3. Whenever x is very large. So in this situation, as you are probably already used to, what do we write? We will write that the limit as x approaches, because I'm saying very large, as x approaches positive infinity of f of x, we will write that this limit equals 3. And all we are saying is, look, the values of this function are getting close to this number whenever this x, whenever the input is very big. That's all we're saying with this. Okay? And if we want to go from negative to negative infinity, we'll still say that the answer is 3, right? Because here it didn't matter. you okay with this? Okay, so we call this limit at infinity. Okay, so let me write down the definition. So let me say similarly, by the above discussion, it follows that the limit as x approaches negative infinity of the function was also equal to 3. Okay, so definition, and so this is limit at infinity, and again this is an informal one, because a formal one has inequalities and a bunch of stuff in there, but we're not going to be doing much with those inequalities. Whenever we need them, then I'm going to come back and tell you something about it, but I don't want you to get confused. For example, if you're studying mathematics, we should not do the informal one. The informal is just, understand what it is, so it's the sentence that I just wrote above. But the formal one involves inequalities, like how do you say mathematically that the values of the function are getting close to 3? And how do you say that something is becoming very, very big? And then this is just a bunch of inequalities that you would write. Okay? So if you're curious, I can tell you later, but I don't want to use time on that. Okay? So if you want, you can ask me after class, and then I will tell. All right. So what's the definition? So given a function, given a function f of x, and a number L, expression limit as x approaches positive infinity of f of x equals L. So what this means, so it means that the values of f approach L. So when I say approach, it means they get closer and closer to L. Okay? Approach L whenever x is very big in the positive direction. When I say very big, I mean in the positive direction. So, as x approaches positive infinity. And then similarly, that's number 1. Number 2, limit as x approaches negative infinity of f of x equals L means that the values of f, the same thing. Same thing as above, but then whenever x is very small in the negative direction. It sounds strange, but remember, it's really small because the more negative you are, the smaller is the number. So that's what we mean by x approaching negative infinity. Okay? Okay, so collectively, remember, this is referred to as the end behavior of the function. So 1 plus 2 is referred to, so it's referred as, the combination. That's why I say is. It's one thing. The combination is referred as the end behavior. Of f. Okay? And that will be important for us when it comes to time to graph. So let me, I guess, say here, moreover, the line y equals L is called a horizontal asymptote of f. Okay, so that's the definition of horizontal asymptote right here. If you want to find where a function has horizontal asymptotes or not, this is what you need to do. Take the limit at infinity and see if you get a number. If you get a number, you get yourself a horizontal asymptote. You don't get a number, there is no horizontal asymptote. Okay, so let's see, samples. Let's do some easy examples first. Let's do the limit as x approaches infinity. When I say infinity, it means positive infinity. Okay. Of 5 minus 2x squared. This is the limit as x approaches infinity of 3 over e to the x. And let's do the limit as x approaches negative infinity of 3 over e to the x. All right, so here we have three functions, and we are computing type of limits. Let's see, the first one. Once again, here there is little calculation to do, okay? It's just analyzing just like before. What's the answer for the first one? 5, good. Why? What happened to the term 2 over x squared? So it goes small, so it goes to 0, right? When we say small, it means here 0. Remember, the top is a 2, and the bottom is going bigger and bigger, so the fraction goes small. So a number over infinity is 0, right? So we get 5 minus 0, which is just 5. Do you understand this? So we would say the line y equals 5 is a horizontal asymptote, okay, in a situation like this. How about number 2? Here it would be very helpful to know what? The graph of e to the x, right? So how does e to the x look like? What's the graph? Exponential function. How do exponential functions look like? If the base is bigger than 1, this is how they look, right? Pass through 1. But let's see, this is the graph of e to the x. Again, you know these basic graphs, okay? They're gonna save you a lot of trouble. All right, so when x approaches positive infinity, so when x is very big, what can we say about e to the x? What's the function doing when we're all the way to the right on the x-axis? Where are we going on the y-axis? Going up to positive infinity, right? So this grows very big. These are exponential functions. Exponential functions, they grow super big, right? But think about 2 to the x. It grows exponentially. You know, there's this famous little exercise. Imagine that you go to a job and they tell you, okay, your salary is gonna be $1 million for this month. Or I'm gonna give you a cent the first day. And then the next day I'm gonna double what I gave you the previous day. So then the next day I give you 2 cents. Then I'm gonna give you 4 cents. Then I'm gonna give you 8 cents. And so on. Yes? Which one of the 2 choices do you pick?
The cents.
So you should pick the cent choices. At the end of the day, you're gonna have like, I'm not sure if it's billion, but it could be close to $1 billion, or definitely more than 1 million would be your salary at the end of the 30 days. Of course, if the owner is, if the guy is a serious guy and is true to his word, right? Because what if after the 10th day he just disappears, right? But assuming that, you know, everybody's honest here, this doubling effect is really fast, okay? It's really fast. And like in computer science, that's why when you want to look for something, we like to have an organized list. Why is it very easy to have another list? When you have another list, it's very fast to find something. Why is that? Because you can have the list all the time. You're looking for a number, you don't have to go through the entire list to find the number. Just cut it in half and then compare your number with the middle. If it's less, you know it's in this half. If it's bigger, it's in this half, and then you look in this half, and then you repeat this. How many times do you need to have? Log base 2, because it's the opposite of the exponential. And log, the exponential is very fast, the logarithm is very slow. So you will only need to do a couple of cuts before you find your element, okay? So, okay, anyways, in this case, when x approaches infinity, the bottom goes to infinity, so it's 3 over infinity. What's the answer? 0. Yes? So once again, do we have a horizontal asymptote for this function? What is it? Y equals 3. Y equals 0. So y equals 0 will be a horizontal asymptote. Okay? Good. How about number 3? Same function, because now we are going to negative infinity. What's the answer? Which one? Good. Again, the question is, what about e to the x when x approaches negative infinity? There's no other x here, so really the question is, what about this guy? Well, look at the graph. What happens when x approaches negative infinity? What's the function doing? Going this way, right? X approaches negative infinity. So what do you see the function doing? It's going towards 0. Yes? Do you understand this? So the bottom approaches 0, and we are approaching 0 with positive numbers. Exponentials are always positive. So a number divided by 0, by something approaching 0, is infinity, right? But because the bottom is positive and the top is positive, we get positive infinity. So you could have a limit at infinity that gives you infinity. Okay, so that's could happen here. Are you okay with this? All right, so there is a special class of functions that it's kind of nice to find the limits. So those are the rational functions. So limits of rational functions. It's like the example that we had at the beginning. So find the limits, and of course at infinity. Okay. So find the limits. Let's see. Let's do limit as x approaches positive infinity of 2x plus 5 over 3x squared plus 1. Then let's do the limit as x approaches. I'm going to do positive infinity, but whatever. Yeah, it doesn't matter. It doesn't matter whether it's positive or negative infinity. It's going to be the same thing. So let's do 2x squared plus 5 over 3x squared plus 1. I'm just going to do negative infinity here, just for the sake of it. Example here, it will matter, the end behavior, as you will see. But in the others, it's not going to matter. So notice that what's important about each of these examples is the situations are different in each of them, right? In the first one, we have a rational function in which the degree of the top is less than the bottom, right? In the second example, the degrees are the same. In the third example, the degree of the top is bigger than the bottom. Do you see this? Let's see what happens in each of these cases. The point is that whatever we do in these cases is exactly the same thing that you do every single time that a situation like this arises. So at the end of the day, it's just the degrees what tells you what's going to happen. Okay? All right, so in the top, once again, that's just infinity over infinity, right? But the question is, okay, which one here is bigger? Is there a bigger infinity, or maybe they are more or less the same like before that we got a number? Okay? It turns out that the bottom is a bigger infinity because it's growing faster. It's a square, while the top is a linear one. So we're expecting this to be a 0. But let's see. Let's let this happen for us. Again, you should divide top and bottom by the highest power in the denominator. But instead of doing that, what I'm going to do is I'm just going to factor. Okay? I think it's easier to just do that. To factor. So I'm going to factor the highest power in the top, which is x. If you factor out an x, what's left? 2 plus, and then 5 over x. Because remember, since we don't have any x in here, then that means I need to divide by x, right? Because when you distribute this x back, you get your top. Do you understand this? Factoring is just the equivalent of division in the same expression. I'm going to do the same thing in the bottom. I'm going to factor out the highest power, which is x squared. Who can tell me what we get in the parentheses? 3 plus 1 over x squared. Good. Why did we do that? Because now we can simplify, right? Now this x cancel with one of the x's that we have here. So we are left with 2 plus 5 over x over 3 plus 1 over x squared times x. X times 3 plus 1 over x squared. Okay, so what is this limit? What happens in the top? Let's see, we see a bunch of little fractions, right? So let's analyze those. So 5 over x, what happens to that one? It goes to 0. 1 over x squared, what happens to this one? It goes to 0 as well. Now, the top approaches 2, right? 2 plus 0. And what happens to the bottom? The parenthesis approaches 3, but here is an infinity. Right? So, we have a number on top, infinity in the bottom. So, what's the final answer? So, we have the top approaches 2, the bottom approaches positive infinity. 2 over infinity as a 0. And notice that what just happened, because the degree of the top is less than the bottom, when you factor out the highest power, that will always cancel completely with the denominator, but there will be something left over in the bottom, because the degree of the bottom was larger, so you had more x's. Do you understand this? If this was a 4 and this was a 20, when I factor, I will have an x to the 4 here and an x to the 20 here. Yes? You will simplify, there will still be 16 x's left over down here. So you are not going to get infinity in the top anymore, because there is no x that will give you infinity in the top, but the bottom you still have your infinity. So number over infinity, you will get 0. Moral of the story, if the degree of the top is less than the bottom, that's always the answer. 0. Do you understand this? Okay, now, next case. Degrees are the same. What's going to happen? We're going to factor. Because the degrees are the same, we have the same amount of x's after we factor. That will cancel out, and then what's going to survive are these leading coefficients right here. Right? Because the other little fractions that we get, that will go to 0 anyways. Okay? So at the end of the day, it's going to be very straightforward. So here we just factor. I'm going to factor the x squared, again, because I have infinity over infinity. Okay? Let me write this as 5x plus 3. Just so you see, how the factoring works. So I take out x squared, there's a 2 left over. What's left in the middle term? If I take out x squared, it will be 5x over x squared, and x cancels with x squared, so it's 5 over x, right? So I'm taking out 2 x's. Here is 1 and 1 off. So I have to divide by whatever I'm off. Okay? That's the point. Here, I don't have anything, so I have to divide by the whole thing. Do you understand? Okay. So 5 over x, and then 3 over x squared. The point is that because the other terms are lower degree, there will always be some x in the bottom when you do this factor. Okay? That's why we do it. Okay? That's how it looks like after we factor. But then these guys cancel. Okay? So they're gone. I'm not going to write, technically you should write another line with this only, but let's just keep it like that. So these two guys, they cancel completely. And then when you take the limit, what happens to all those little fractions? They all go to 0, right? Because the x's are only in the bottom. So what survives in the top? A 2, and in the bottom? A 3. So you get 2 over 3. Which happens to be the ratio of the leading coefficients. Hopefully this starts ringing the bell to you back from when you learn this, right? Degrees are the same, you just look at the ratio of the leading coefficients. When the degree of the top is less than the bottom, the answer is 0. Okay? And in this case, and again, I'm going to do the same thing. I'm going to take out my x cubed. So I get 2 plus 5 over x cubed. And then here I take out my x squared. So I get 2 plus 1 over x squared. Notice that because the top now has a larger degree, what's going to happen is that after you simplify, there will remain an x in the numerator. Yes? So this time, the bottom, there's an x that remains on top. So this time the bottom will approach a number, namely the number 2, right? But the top still gonna go to infinity. Like in this case, go to negative infinity. By infinity divided by a number, still infinity, right? So now this piece goes to 0, this piece goes to 0, but then this top right here is gonna go to negative infinity. So the answer here is negative infinity times 2, so it's still negative infinity, and the bottom is a 2, so that will just be negative infinity. Okay? So moral of the story, when you have a rational function, there are only 3 cases, and it's just look at degrees. If the degree of the top is less than the bottom, 0 is the limit at infinity. If the degrees are the same, it's going to be the ratio of the leading coefficients. Okay? And if the degree of the top is bigger than the bottom, then it's going to be infinity, either positive or negative. Which one is it? You know, it depends on the sign of these numbers, and then you need to analyze what's happening here. Okay? But you know it's going to get an infinity. And then just do this. And by the way, there is something else. As you can see, did any of these terms play any role in my limits? The 5, the 1, the 5x, the 3. Do we really care about those? They don't matter, because after we did the factoring, they all end up with x's in the bottom, and they all go to 0 anyways, right? So we call that the trash. Okay? There's something called the garbage rule that basically calls those guys garbage. And then when you're finding the limit at infinity, a function like this, all that matters are really the leading terms. So typically, and then I guess that's a faster way of doing it. For example, for the first one, applying the so-called garbage rule, you will say, okay, I know that all the lower degree terms are garbage, so I'm just going to ignore them because the limit is not going to change. And then we keep what matters. Okay? So you ignore everything else, and then you keep the leading terms. And the limits are going to be the same. Whatever this limit is, will be the same as this one. And this comes back to something that you learned in pre-calc that says that for polynomials, the end behavior of a polynomial is given by the end behavior of its leading term. That's all we're doing. We're just looking at the leading terms of the top and the bottom. And now here you do simplify, and then you see that this is 2 over 3x. And now, clearly, this will be 0, right? And same thing for the others, you can play the same game, okay? So if you don't want to memorize the theorem that says just look at degrees, and depending on the degrees, that's the answer, what you can do always is apply the little garbage rule. Just, look at the leading terms and then simplify quickly, and that's it. That's faster than doing what we just did. But we need to do this first so you can understand why it works, okay? Because the other guys, they play no role in the limit. You okay with this? All right. So, okay, I'm going to leave a space here because I don't want to use the 5 minutes that I have to write down the theorem. I want to do 2 more examples. So I'm going to leave a space to write the theorem. The theorem that I'm going to write is what I said out loud, the description of the degrees. The degree of the top is less than the bottom. The answer is 0. Degrees are the same. The answer is a ratio of the leading coefficients. The degree of the top is bigger than the bottom. Then the answer is either positive or negative infinity. Okay? I will write it down, but later. So I'm going to leave a space here. And I want to do an example of finding horizontal asymptotes. So find horizontal asymptotes. And function that I want is, let's see, 4x squared plus 3, or 7x squared minus 7. And then the other function is going to be 1 over 1 plus e to a negative x. Here we have 2 functions. Let's find the horizontal asymptote. Horizontal asymptote is easier than vertical asymptotes. Why? Because for vertical asymptote, you have to think about the candidates. What x you need to approach to that will give you infinity. So you have to come up with those numbers, okay? For horizontal asymptotes, all you do is take limits at infinity. You take the limit as to positive infinity and to negative infinity, and you observe. If you get a number, you find it. You don't get a number, there's no horizontal asymptote. Do you understand this? So you just go ahead and quickly compute. There's no candidates to consider here. So it's easier this way. Okay, so for the first one, we're gonna do the limit as x approaches positive infinity of the function, and then we will also do the limit as x approaches negative infinity of the function. Let's see. In this case, our function is a rational function, so we can use the theorem that I just mentioned. What's the answer here?
4/7.
Be 4/7, right? Just look at the degrees. Degrees are the same, so the limit is the ratio of the leading coefficients. 4/7. Do you understand this? That's because degrees are the same, so it will be 4/7. You can do the garbage routine, and then the x squares cancel, right? And you get your 4/7. Okay, so that means that we found a horizontal asymptote. So that means that the line y equals 4/7 is a horizontal asymptote. Okay? All right, the next one. That's the limit as x approaches negative infinity of the same function. Once again, what we did above, it works to either positive or negative infinity. It doesn't matter. Same story. If you do your garbage rule, this guy cancels, and you still get your 4/7, right? So same degree, so ratio of leading coefficient. 4/7. So this reinforces that we have a horizontal asymptote, but actually we know there's a horizontal asymptote on both directions. Okay? So when x approaches positive infinity, our function will get close to 4/7. Similarly, when x approaches negative infinity. Typically what happens is that it could be that we are doing it from above in one sense and then from below in the other sense. Think about 1/x, here it is. Y equals 0 is your horizontal asymptote now because, for example, this one, 4/x. Degree of the top is 0 and the bottom is 1. So the top is smaller, right, the degree. So the answer, the limit would be 0. It's just that when you go to positive infinity, you go to 0 from above with positive numbers. And when you go to negative infinity, you go to 0 from below with negative numbers. Okay? And how about the last one? That this one is not a rational function, so that theorem does not apply. Okay? Here you do need to compute because this is not a rational function. You know, there's no notion of degrees per se in here. Let's see. The first limit. Who can tell me what's the answer? 0. Why is that?
Got 1.
Good. So x approaches positive infinity. But what do you have here? A negative. So this is actually approaching negative infinity. Yes? So when the argument of the exponential approaches negative infinity, what's exponential doing? It's going to 0, right? Again, look at the graph. When the argument, the stuff that you're doing, e to that whatever, when that thing approaches negative infinity, your values go to 0, right? So, in this case, x, I understand x approaches positive infinity, but we don't have e to the x, we have e to the negative x. Okay? So when x is positive infinity, negative x is negative infinity actually. So this is 0, so you get 1 over 1 plus 0, which is 1. So that means y equals 1 is a horizontal asymptote. How about the other limit? What is it? 0. Be careful. X approaches negative infinity. What happens to this one? It's positive infinity. E to the positive infinity is positive infinity, but that's in the bottom. What's 1 over infinity? 0. Have to be careful. Do you understand this? This one went to positive infinity, but that's in the denominator. The top is a 1, so 1 over infinity is 0. So we found ourselves another horizontal asymptote. This means the line y equals 0 is a horizontal asymptote as well. So what's happening here is that for this function, even if you have no idea how it looks, here is 1, 0 is the x-axis. You know, what happens is that this function is trapped between, you know, it's in here, doing whatever, but it's trapped between these two lines. Okay? It cannot go beyond 1 or below 0. It's between those two. At some point, we're going to understand precisely how it looks. Okay? What happens in here? But now we have some information on it. Okay? And actually, we have more. We know that it does this and it does this, right? Because this was a negative infinity, so it has to go to 0 like that. And that one was a positive infinity, so it goes to 1 like that. If you need to guess, how will it look like? What will be your guess? How do you think it's going to look like? I mean, there's only one reasonable thing to do, something like that. Okay? Again, we're going to figure this out once we know more, right? Okay, so